Good morning again. How are you all? Survived the first 2 weeks and looking forward to the rest of it, yeah? All right, so, okay. So tell me about the first 2 weeks. How were the labs last week? Who understood them? Who were able to work it out with solutions?
Yeah, I had a lot of questions but I had a quick look at the solutions today. What I was after was the methodology, approach of how to eliminate variables.
Which question are you looking at? Question 1, question 2, or question 3?
Actually the fitting in general.
Yeah. So question 1 and 2 are more on R related stuff, right? So entering data in R, at least for the first 2 questions, should not have been that difficult, at least with solutions to understand. You have to create the variables that you need and then enter the data into those variables. So first of all, you have to create those categorical variables. For example, in the first one is temperature and material in the right kind of sequence, and then enter the data in the third column, yeah? That does it. For the second one, yes, you can enter the data in a similar way. But the second one was a bit more difficult because then you have to unravel the data to make it a one case observation, right? That's more tricky. As I was saying earlier, that's far more useful than looking at the table that way, because the table data as we had for the second one, for the seat belt, we can do some very simple analysis with that. We can't do anything more advanced. But if you unravel the data to get one case per accident, then you can do a bit more with that, and in fact quite a bit more with that, as we'll see. Yeah. So those two are the difficult ones. Model fitting for the last one. For those who did STAT2401, which ones? Who did STAT2401? Then you should know that already. Is that true? You've seen that before.
We didn't make a data frame, but we're familiar with the R function.
So you can fit the model,
yeah,
and you can reduce the model. Yeah. All right. For those who haven't done that, well, in that case, there's need for you, and we'll cover these things over time as we go through. So you'll get more used to the idea. So you've seen the lecture notes from last week. You've seen the lab and solutions from last week as well. You have the test due this week. Note that with the test, what we're looking for is not a correct or best model, right? Because in these situations with data that is, in fact, quite complicated, it might look simple. It's not actually that simple at all. It's rather complex data with the observations you've got. And the other thing with the data is it's got quite a bit of variation. As you plot the data, you'll see them. It's lots of variation there, which means model fitting is more difficult with that kind of data. And what we are looking for is going to be some ideas of fitting the model to start off with, and model diagnostics to check whether the model is going to be good enough, not good enough, how do I modify it, and model reduction from there, taking out variables, right? So model fitting, as far as what we did last week was concerned, deciding what kind of transformations to use takes a bit of nuance, a bit of experience. But looking at the data, you'll be able to pick out whether it's square root or square or log or something of that kind. Now, I might use square root, you might use log, yeah? And there mightn't be too much difference between those. In some situations, maybe the log's better, sometimes maybe the square root's better. And we can compare models, and we'll try and do some of that today and show you how that works over time as well. But other than that, if you show me evidence of having done all that, you will get the marks. Your model mightn't be the same as mine. It doesn't matter. Yours might be the same as his. It doesn't matter, right? You do your own stuff and use those ideas to get those modeling things out of the way. In other words, do the first model, work out what's wrong with it, how do you fix it the best you can, and take some of the non-significant variables out, get some model, and you're done. Step by step. Yes, Mr. Singh.
You know when you've done the summary and you see that there's some really high p-values, right? And then you look at the interaction of variables and other responses.
Yeah.
At what point do you have to transform that, or do you just get rid of it because the p-values?
Once you fit the first model, right, the p-values at this stage don't make any sense at all. Right. They don't have any, in my opinion, particular strong meaning at the moment because you haven't seen the diagnostics yet. Right, your model may be where it looks like a square and you fit it a straight line. It might look very good. Yeah. So what you need to do is look at the diagnostics. So you've got the plots of the response variable against each of the other variables to see what the relationship might be like. Then you've done the first modeling, you look at the residuals from there, you've plotted the residuals against fitted values and against each of the other values to see what's going on there, to see what the pattern might look like. And from there, you'll pick up any other transformations of the data. Yeah? Okay, we'll get to that. Get to that in a second. Yeah, so again, those are the things they should be trying to do. Now, I have no problems with you working in groups together to work out these ideas, but your submission must be your own. Your work must be your own in the end, right? You might discuss all of that with this plot here. What have you got? Okay, how do you transform that? What do I transform this as? You can discuss that, that's fine. I presume you might do some of that in the lab in this week or so, and that's fine. You can ask demonstrators. They might give you some very broad answers. They won't give you solutions because they don't have the answers. They haven't got my answers, at least. And I say, if I make the demonstrators do the same kind of work, they might find some other model. Sometimes there's a choice to be made. When you try and reduce the model, you've got p-values, so you pick the largest p-value, bigger than 0.05, and remove that variable first, right? That's the general rule, but sometimes you might choose otherwise. In particular context, you might think this variable is important. I'll hang on to it as long as I can. So you won't remove the thing straight away. You'll try and keep that and remove other variables instead. You might find in some situations where taking one variable out makes your model far worse. So you keep it in, although it's not significant. You don't know why this is the case. You can do all kinds of plots to see what's going on here, and you might pick anything up. So in that case, you keep the thing in there, but you don't report that it's significant. Yeah, this is how sometimes modeling works. It's just because, sometimes with complex data with 4, 5, 6 variables, especially categorical variables, you can have interaction terms in there as well, and what kind of interactions actually are significant, which ones aren't, sometimes take a bit of working out. Yeah, and so I don't want you to get lost in that. Do try some interactions as you go through. If you've got lots of categorical variables, at least 2 or 3, for example, if I've got, looking at, say, this weight and height example as well, I've got weight, I've got height, and I've got gender of the person as well, and I've also got, say, ethnic group. Yeah, and I've got ethnic groups as being broad, Caucasian, indigenous, others, let's say. Then I certainly want to look at the interaction between gender and the racial groups there, ethnic groups there, yeah, in case there's something there, because you might find that, look at, not being racist anyway, look at Africans. They're built like that. Tall, skinny like anything. I've got neighbors from Africa next door to me in Brisbane. And you look at, they're sort of, built like a lamppost, straight and tiny, and really, so they're tall, but they're really skinny, yeah? As opposed to somebody who may be tall and well-built, or even short and well-built in some other ways. So you can't judge that in that sense. And again, you look at other things as well. For example, you look at 2 people who look exactly the same on the outside, but one is very athletic. So what they're made of is their girth and everything is just as full of muscle. The other guy is not so full of muscle, right? So their weight's going to be quite different. People have bigger bones as well. That makes a difference as well. So you can't just tell. So yes, certainly in those kinds, you'll put interactions in there to see that's significant. Yeah, interactions. In that case, you can put in interactions between 3 variables if you wish, but it gets more complicated to interpret them. 2 interactions is probably as maximum as it'll go. Sometimes 3, but it makes the model more complex. You're far better off in that case if you're going to have 3 interactions to subset the variable. In other words, stratify it and say, all right, instead of taking a look at 3 interactions, I'll take that 1/3 variable and look at one level of that, and we'll build a model just for that with a 2 interaction. Another level, do something else with that to see how it works. And sometimes what you find is that one level doesn't have much data anyway, so you can easily remove that particular level and fit the rest of them in there. Any more questions before we carry on? All right, so we've, a few things to cover today. As you know, I'm trying to revise the course from the last time I taught it 2 years ago, and so that's taking me a bit more time to prepare the lecture notes. But I'll go through the lecture notes first today, and as we go through this, I'll pick up on some other things. But before that, I do want to try something else, and this is what I want to look at. You asked me about categorical variables. So if I've got this weight and height example again, so I'm trying to predict the weight of the person based on height. And so the model is going to be some constant, or the my intercepts term, beta naught. And I've got another one here that will be with the height of the person. Now, I also want to include gender now, male, female. So I've got 2 levels of that. So I'm going to have here the beta 2 male. Now let me put in also beta 3 female. If I'm taking a look at the weight of a male person, then my equation is going to be weight equals beta naught plus beta 1 times height plus beta 2 times male. And if I'm looking at a female person, then my equation for weight for that person is beta naught plus beta 1 height plus beta 3 female. And so the problem I find there straight away is this. I've got this beta naught here in both of those. So, and I've got this beta 2 here as well and beta 3 here. If I was to add a 10 to beta naught and take 10 off beta 2 and take 10 off beta 3, I have exactly the same model. In other words, the beta naught is an extra I don't need in that. In fact, this kind of model is what we call is over-parameterized. I can't estimate it because essentially I can reduce beta naught by 10. If I add 10 here and take 10 off from there, I have the same equation. So I can't estimate that to a particular number because, in other words, I have some problem here. So the better kind of model we build there is we say, well, our interest actually isn't in beta naught anymore as such. I am more interested to see what's the difference between male and female. So R does this automatically. If you put in, say, a variable with gender in there, and it's got male and female in there, in the model equation on the output in the summary, you will see only one of those, either male or female. And what R does is it selects one level as a reference and compares the other with it. So what we should have is, taking a look at a better model, or the model that we should be fitting is going to be weight equals beta naught as my intercept plus beta 1 times height. And by default, R will pick the variable from the categorical variables in order of, in alphabetical order. So with male, female, it will take female as a reference and put male in the model by default. So it's got gender has male and female. And as I say, because it all works by default in alphabetical order, it will take the female as a reference level. And compare male to that. So given this particular model equation now, for a male person, my model is weight equals beta naught plus beta 1 height plus beta 2. And for a female person, it is weight equals beta naught plus beta 1 height. So the difference here is beta 2. Beta 2 is the difference in mean heights between male and female. Mean weights, I mean, sorry. And if you like, I'm really saying that beta 2 is the extra height for males. Extra meaning essentially as a term there. If it was negative, means males on average weigh less than females. If it was positive, that means on average they weigh more than males. And my model here essentially, if I reduce the model by taking out the male, the gender part of it, right? So if I reduce the model and say essentially I'm testing the hypothesis, I'm looking to see essentially that beta 2 is equal to 0. That means there's no difference between male and females. And H1 says beta 2 is not equal to 0. In other words, there is some difference between male and female heights, between female weights. Is that clearer and better? If I've got something with 3 levels, it takes 1 level, the level in alphabetical order is reference, and you'll have 2 things in the model equation. You'll find 2 entries there in your summary of the model. That's how it works. You can reorder them, and sometimes you want to reorder them. So, for example, you've got something like, I'm looking at levels of nitrogen or whatever else. You've got low and medium and high. By default, H being the lowest in alphabetical order becomes the reference. You've got low, medium compared to that. What you might want to do actually is use this as reference. And then you want to compare the medium and high with that. In other words, you've got this hierarchy there now. Low, I want to see how much different medium is from low and how much difference high is from low as well. So you might reorder that, and you can just search on Google to see how you can reorder factors. So go R in Google, reorder factor, you'll get the whole thing on there. Cut, paste, change the code, you've got it. So I'm encouraging you to learn to look and search for things like we always do. We don't know everything about R. I keep forgetting stuff. I keep reusing code, as I said before. And so just look it up again. It's far easier than hunting through lecture notes or whatever else or asking somebody. Bang, here it is in 5 seconds. You've got the thing. Cut, paste, you've got it. And while you search for these things, you'll find more sometimes there than you wanted to look at. And that's also useful to learn as you go through with this. Any questions with this? All right, then the next thing I want to do is take a look at this R Markdown stuff that I have the notes on there for. So what R Markdown does is, R is very clever in this way, and how this is developed is, I can produce reports from within R straight away. So here's one, lecture 3 it says, I've got a title there, I've got these 3 dashed there, it actually separates things from the R code, if you like, and the rest of the document. So this is the title part of it. So I've got here the title, the author, the date here, and output here with this. The next things come in. I want a colon only in one line. I can have 2 colons there in the same line. That's why I'll start this in the next one, and so on and so forth. It's an article style document I'm after here. This is some initial setup stuff that you can just copy and paste, and you'll learn more about this if you want to search them. Otherwise, you can just use the thing as it is. So this is my comment. It's R Markdown. This is R Markdown document. I'm telling you what it is all about. Here are my R commands. The way that they come about is with these quotation marks. And I put in here the R commands and end by quotation marks. And you can see what I've got here. I've got plots over there. So this is R figure environment. I've got a caption here for the plot. I've got a label for this. This is pressure. It says plot pressure. It'll plot that for me. And then I've got later some mathematical stuff there. Just this is more LaTeX stuff that you probably will not know much yet, but you can learn if you want to. Very simple indeed. So I've got a begin equation. I've got sum here from 1 to n of all the rest of it. And to actually typeset the whole thing, all I do is I go to this knit over here, and that comes up here whenever I've got an R document of this kind here, which I can convert. And I can simply either knit it or I can convert to PDF. If I convert a PDF, it produces from there a PDF file straight away. Now, I look at this, and I mightn't like it. Did it actually do that? Yep, there's my PDF document here, straight away. So I look at this and I don't like it at all. I want to change some things. I want to, oh, this, I didn't want this between, I wanted a 3 there instead. I go back and make that 3. More than that, I don't like the plot here. I want to change the temperature to an uppercase T. It's simple. I just go back in the document and change that to uppercase T, and I can get that done. Now, the thing with doing it this way is that I have got essentially, if you like, a live document preparation scheme. Often you prepare documents here and you do the R thing differently from the document. You go back to the document 3 weeks time and you change the figure or something. If you go back to R, now I guarantee you in 3 weeks you'll forget where the data was, what data you had, what did you do with this. Sometimes you forget the code as well. What was I trying to do there with this code here? Sometimes the code escapes you all of a sudden. Sometimes you use some clever coding and you say, what was going on there? I don't get it. Whereas if it's in the document itself, you know where the document is, you know the data is available right there. If you change the data, it still links up with that file straight away. It's much easier, and you can produce the plot straight away. It's far easier than if you've got a big R code with something like 10, 15, 20 figures, and searching through to find the figure that you want. It's much more difficult than having the thing available with you right there. So I encourage you to try these kinds of things with your actual assignment, because in the assignment you're going to be doing things like summaries. So here I've got a summary of that straight away, and here's the output as well. No cutting and pasting anymore. The output's available to me straight away. I can see the R command you use. You're trying to fit a linear model over here. Here's the model. Here's the output of the model. Here's a graph of the residuals with the fit values. All those things available to you straight away. You change the model, all of a sudden you say, oh look, I didn't actually want this. I wanted the model to have, instead of circumference, I want the circumference squared. Square the thing here, bang, it comes out straight away in the document itself. Now doing the thing there, cutting and pasting, all the rest of it. So you can modify this code as you go through and fit your models, and everything comes out in sequence. And you can present it straight away. With there's your writing all gone, yes.
So would you recommend that we create a new R script for each assignment, for example?
Absolutely, I'd recommend that. I'd recommend that, yeah. And of course, you can use the old one and modify it once you've got the basic structure done, yeah. So things like, for example, these R things that are in there, you know, I wouldn't mess with much of this. I'll just change the date if I like it, maybe the author, whatever else, and the title, but I'll just keep the front end the same. And as I go and change the R code over here, I'll just change these things as I go through. I'm not going to mess with that very much here. So it's actually far much easier to do this kind of stuff in R directly. So I encourage you to try it, attempt it. You'll find it's not so difficult. It'll make your life much easier. Excuse me. Especially if you can work with data science and data analysis, get used to these kind of ideas. They really save you time. And it puts you ahead of the pack who are doing this, the old sort of cut and paste away from R into a Word document and all those kinds of things go crazy and queer. Yeah? In fact, of course, I'm sure it's pretty clear to you, we produce these documents here, our lecture notes, are in R straight away. Yeah, that's why you find these kinds of R things in there very easily. So all the plots and the graphs and the R commands are straight away in the document. I don't have to go and find the thing somewhere else and do all the hard work and then cut and paste. It makes it far easier if I do it straight away as it is. So all of us do this kind of stuff, and this is far much easier. And it's easy to pass to somewhere else saying, here's one document, everything's in there. Just modify that, you've got it. So try that, please. Let's go into the lecture notes here this week. So we'll go back a little bit this week and try some simpler things and work through things in detail. So some things you saw last week with R, you would have, in the R lecture notes in the week before, you have found to be a bit obtuse. You wouldn't have seen some of those. Well, let's have a look at these two again. So here's a question. We're looking at proportions this week. So proportions really means the percentage of population or proportion of population that has a particular characteristic or whatever else. So here we're looking to see, there's a referendum in 2009 on daylight saving in Australia. And so the idea is the referendum will guide us to whether the population, more of the population, 50% or more, actually is in favor of daylight saving or not. So this is the question: do you want daylight saving here to start from October and go till March or so in the following year? Yes and no here. So proportions is the fraction, if you like, a percentage of the population that actually has a certain attribute. If I've got A is the number of successes, and success is generic here, success meaning people have answered just to the question I'm asking here, and B is the number of failures, proportion of successes is going to be A over A plus B. So A plus B is my total number in my sample, or total number of people I've surveyed, and A is the number of successes. That's my A over A plus B. So in the referendum, actually, what happened was that the yes vote was 519,000 or so, and the no was only just a little bit more than that. So otherwise, it came out to about 45% who said they didn't want, well, only 45% said they did want daylight saving, and so daylight saving was not implemented. I think this was the third or fourth referendum they had this on this NWA. Right, so you'll find the data here in that website. What if I want to do a poll first? Before the referendum is actually held, like elections are held, I want to have a poll there to gauge the success, possibility of success, or gauge the proportion of population who are in favor of a particular situation or stance. So I randomly select 1,000 voting adults in WA, and I ask them each of them the same question: are they in favor of daylight saving or not? And they say yes or no. And suppose in the sample I get 480 who actually agree with me, who want daylight saving. Now the thing is, the sample isn't my whole population, so I'm going to have some variation there. In other words, depending on what my sample is going to be like, some samples will have, if the population is exactly 50%, when I sample people, I won't get exactly 50%. It's like saying the probability of heads is 0.5, and I toss a coin 10 times. I won't get exactly 5 heads. I'll get sometimes 4, sometimes 7, sometimes 3. So the point is it still expected to get 3, 4, or 5, or 7 heads if probability of heads is 0.5? Is it still likely to get that? That's the kind of thing I have to judge here. So in my sample, if I get 480 people saying that they are in support of supporting daylight saving here, does that mean I do have support or don't have support? In other words, is this possible to get 480 from this kind of sampling when proportion of people who actually say yes is actually 0.5 or bigger? But 0.5 is a boundary line. I'll take 0.5. Is it possible to get that? If I toss a coin 10 times and probability of heads is 0.5, can I get 7 heads? How possible, how likely is that going to be? And I can judge that by saying, all right, if I do toss a coin 10 times and I get 7 heads, and probability of getting 7 heads when probability of heads is 0.5 is 10%, well, that's all right. It's okay. It's not too small or too big, or not too small in a sense. If I only get the thing as 1%, I might begin to doubt it, right? Maybe 1% is too small. So the question here is, when I say 10% is not too small, you might argue with me. Somebody else might say 10% is small. Some might say that 20% is small. So we need some idea what small means to start off with. So we'll get to those ideas as we go through here. So I'm trying to infer here from my sample, is 480 people enough to say, oh, hang on, that means that the referendum, in other words, what I'm saying is, what I'm seeing in the sample, if this reflects what the population says, then 480 isn't enough to support daylight saving. That will be my conclusion if I decide this is the case. So I need to infer that. I need to infer what my population is going to be like based on my sample. In other words, I'm saying what I'm seeing in my sample is what I'll be seeing in my population at large as well. So I can view the true proportion of the population who voted yes to this particular question as a probability, and I can look at this in a formal hypothesis testing sense, and I'll do all that. There's two things we'll do here. One is to look at some inference kind of ideas, so some hypothesis testing, and the second is some estimation here to work out some values I can get from my sample for the probability of a yes vote for daylight saving. So I require some kind of model over here, and the thing with a model is it is able to describe for me the data generation mechanism. In statistics, I'm looking to see is my data generation mechanism, what is it like? And then I can look from there to estimators and the properties of estimators, and then from there I can go in and do more statistics. So we'll see those ideas as we go through here. So estimator here is a functional procedure, or it's essentially a random variable here, and the value for that I get from my data, once I've got my data, I can find what's called an estimate. So these things, things like estimate and estimate and probability and statistics have particular meanings. They aren't the same. Estimate is a random variable. Estimate is a particular value of that. Excuse me. And I know the terminology is a bit similar and a bit sometimes maybe might think a bit confusing in the beginning, but you'll get used to this as we go through here. And the sampling distribution is some probability distribution I get before I can proceed with things. We'll see how that works later on. So what we're going to do here is, we saw last week some distributions. Essentially what we got is a trial which says yes or no, success or failure, like tossing a coin. In this case, the voter says yes or no, and that's a Bernoulli random variable. So Bernoulli meaning it takes only values 0 and 1. 1 is success, 0 is failure. Probability of success is pi, and probability of failure is its complement, 1 minus pi. And the probability mass function, we know we can list it if you like. I can put the thing as 0 or 1 for the values of y. The probability here are pi and 1 minus pi. But I can write the thing as an equation as well in this sense. Probability of y equals y, where the values of y are 0, 1 is this. When y is 0 over here, you can see this becomes a 1, and this becomes a 1 minus 0, which is just essentially a 1. I get 1 minus pi. So when y is 0, my probability is 1 minus pi. When y is equal to 1, this is pi to the 1, and this is 1 minus pi to the 0. This is the 1. I get pi from there. This is a nice, neat way of writing the equation for the probability mass function for Bernoulli distribution. It's pi to the y times 1 minus pi to the 1 minus y here. And the only parameter here I have is pi. So parameters are what we have as things are required with the distribution. This Bernoulli distribution has one parameter pi. Once I have pi here, that defines for me the probability mass function. Whatever probability mass function I've got there depends on pi, so I require pi here. That's my parameter. In this case, only one parameter is given to us. We know from last week the mean of the Bernoulli is pi, and the variance is pi times 1 minus pi. So those things I have from last week. Now, we do have this assumption of constant probability with the Bernoulli trials. If I have a certain number of Bernoulli trials, I'm assuming the trials themselves are independent and the probability of success isn't changed. Now, that might not be the case in many situations. Like if I'm taking a look at a deck of cards and I pick a heart, the probability of the next heart is changed already. Likewise with people, if I've got 100 people to sample from, and I'm taking a look at pulling one person out of the sample, and I'm sampling without replacement, I don't sample the same person twice, then if I have 100 only to choose from, when I've taken the first one out, I've only got 99 left now. So if 99 is left, probability of getting somebody who will vote yes has now changed all of a sudden. Now the idea is that if you have repeated trials without replacement, then in fact they're not independent. But you can treat them as independent if your population is large enough. And so the idea is if you're actually sampling only 10% or less of a large finite population, then the Bernoulli trials model can be assumed, your trials can be taken as independent, and your probability of success can be taken as constant. If my population is 100,000, then by the time I've taken one person out, it's changed very little. 950,000 here, for example, here, by the time I've taken one person out, probability of getting that one person with a yes vote is this much. The next is a bit less than that, but really it's not much different. It is one less than that agreed, but it doesn't change much. In other words, the change is so small I can assume that everything is fine and carry on as I would. In other words, my model here, as most models, aren't perfect, but it's good enough in this case. So I can assume here that my Bernoulli trials model holds. The parameters here, as I said, are those that are associated with the probability model I've got. And there are two aspects of inference we look at. The first is hypothesis testing, as we saw earlier, decisions about the value of the model parameter. The second is estimation, which means I'm now actually interested in obtaining the value of the parameter from the observed data. We'll look at both of those today as we go through here. So I want to decide if my sample that I've got from the daylight saving is going to help me here. So essentially what I've got here is I've got a binomial situation. I've got 1,000 trials and 1,000 Bernoulli trials, and I'm counting the number of successes. That makes the number of successes binomial. So x here denotes the number of people in my sample who will vote yes, vote in favor of daylight saving. So x is binomial, 1,000 and pi is probability of success here. If the referendum supports daylight saving, then pi is bigger than or equal to 0.5, otherwise it's not. So what I'm looking at here is in my sample I've got 480 people. Now my question is, what's the probability of getting 480 or less if my probability of success here, my pi actually is 0.5. So I'm testing that the hypothesis I'm testing is pi is 0.5. That's my null hypothesis. I'm actually assuming just out of it that there's no reason to doubt that there's any evidence against at the moment so far that there is no daylight saving support here. So the boundary value is 0.5, so that's my equal value. You could say bigger than equal to, but usually the equality is enough over here for the null hypothesis. And my alternative is there's no support for the daylight saving, so this pi is less than 0.5. Now, of course, I'm looking to see whether there is support in the population for daylight saving. Currently, there isn't support. I haven't got daylight saving, and that's why my hypothesis actually should be this way. And of course, I've also got fewer than 50% here in my data as well, so that also guides me in some way. So I'm going to have a look at this hypothesis testing as I go through. This is my null hypothesis, alternative hypothesis here, based on my data. I'm looking at how likely am I to observe 480 or fewer people in support of daylight saving in my sample. So I've got my probability model over here, and what we base our decision on is this idea of p-value. I'm going to look at the probability of getting the data as extreme as I've got. Extreme in my case is going to be x. I've got 480, so less than or equal to 480. 480 more extreme. And I'm going to see what the likelihood of that is, assuming that my null hypothesis is true. In other words, assuming that pi actually is equal to 0.5. Look at the coin tossing example. If I toss a coin 10 times and I get 3 heads, I want to know what's the probability of 3 or fewer heads if the coin is fair, if probability of heads is 0.5. That's what I call a p-value here. If it's small, we conclude that the observed data and the null hypothesis are inconsistent. In other words, observed data isn't consistent with the null hypothesis. There is no support for the null hypothesis in the observed data. And so this is where I will say that my null hypothesis is going to be rejected. Now, this is a common problem and misunderstanding. This is not a probability that the null hypothesis is true or false, nothing to do with that. It's just a judgment, it's just a criteria based on the data to decide if there is support in the data or evidence in the data for the null hypothesis or against the null hypothesis. So it's not probability that the null hypothesis is true or false, nothing to do with that. Now the idea we had was it's small, and small of course is quite arbitrary. And so what we do is we usually take a look at 0.05 is our significance level for a two-sided test. Now a two-sided test looks like this. H0 says pi equals 0.5 and H1 says pi is not equal to 0.5. In other words, I've got now my extreme data can be either too big or too small. Usually we try and, as much as possible, look at the one-sided test. In other words, I have a particular direction that I'm interested in. In other words, I would rather have pi here as being less than 0.5. I know the direction I'm looking for a change in. So if it's a two-sided test, it's 0.05. If it's a one-sided test, it's half, 0.025. That's really all. And we'll see how that works as we go through here. So this this thing we call significance level, we give it this symbol alpha here. It's a significance level. If the p-value is less than that, we say it's small, and that's when we reject the null hypothesis and say that the data doesn't give us evidence in favor of H0. In other words, it gives us evidence against H0. This idea of significance testing is what you might see quite often being quoted and looked at. And this is where you say if we actually reject the null hypothesis, we say the result is significant. So here in this case my p-value is probability of x being less than or equal to 480, assuming the null hypothesis, in other words assuming p is equal to pi is 0.5, and there's my R code. I get the probability here is 10% almost. So this is bigger than 0.05. Now I should really be looking at 0.025. Yeah, and so I'll change that. It's a one-sided test. It makes it even better in that case. And so here I've got insufficient evidence to reject the null hypothesis because my p-value is large. It's larger than my significance level of 0.025. In other words, here I say that based on this data, I don't find what I'm not missing here. So based on the data, I've got my p-value is large here. So I find that my support for daylight saving in NWA is not less than 50%. And the referendum will not reject the proposal. In other words, if the probability of or the support for daylight saving is 50%, then 480 is not an unlikely value in my sample of size 1,000. And we'll see some more of those ideas as we go through here. I'll stop for a second. Any questions so far? Okay, move on. That was hypothesis testing. Estimation looks at trying to obtain values for the parameter pi. There are two kinds of estimators. One is a point estimator, where you get a single value for the parameter, and the other is an interval estimator, where I can get an interval here, and this is mostly called a confidence interval, and essentially this is the sort of likely values of the parameter. The problem with the point estimator is that it's a single value. It doesn't give me any idea of variation there. It's some estimate of the best estimate I can get, some idea of the best estimate, but as I say, it doesn't give me any idea of variation. How good is my estimator there? That's the thing I'm after here. We'll get to that in a second. And so how do you obtain this best estimate? Well, in the case of a binomial distribution, I can do no better than looking at the sample proportion here. So usually what happens is the sample statistics or the sample quantities become the best estimators. Now there's some maths behind this as well. You might look at some of this later on in the semester. There's some ideas here as to why this is the best estimator. But by and large here, what I've got is if my y's are Bernoulli, independent and identically distributed. I'm sure I mentioned this before somewhere earlier, but the IID means independent and identically distributed. So in other words, they have the same distribution. So if that's the case, if my bar is a Bernoulli with parameter pi, then the point estimator is just the sample proportion. So this is the number of successes on top. Yi is 1 if it is a success, number of successes. And this is number of trials. So this is actually a sample proportion of successes. So I'm taking my estimate of the proportion as the sample proportion. But of course, in this case, this is also the sample mean, because essentially I'm just adding everything up and dividing by the number of observations I've got here. So this is also a sample mean in this case. The thing with the point estimator, so in the case, in my data that I've got there, what I'm going to get is pi here, and use a head for estimate. As pi hat observed is what I'll use right here, because pi hat is my estimator, and pi hat observed from the data I have is 480 over 1000. So that's my estimator, estimate of pi from the data that I've obtained. But the thing is, the point estimates have no information on variation. So, for example, if I take a look at a situation where I've got data 1, my n in this case is 100, and I've got observed number of successes is 48, then my pi hat here is 0.48. If I've got another set of data here, where now I've got 1000, and my observed number of successes is 480, then I again get pi hat is 0.48. But these are quite different because my sample size in the next one is larger. So I expect that to be more accurate. And this is the thing about point estimators versus interval estimators. I'm trying to build in the idea of variation or accuracy in my estimate as well. So one thing I could do is I could quote not just the actual value I'm getting, but also some idea of variation. I can do that. Or I can do a confidence interval calculation. Both of those are equivalent, and we'll see how they work. So the variation here is because of sample size to start with, for example. That's one of it. Or maybe the estimate I'm using is different as well. So the interval estimates have this idea of location, which is what I had as pi hat here, my single point, but also the idea of variation as well. And so before I can work that out, I require the distribution of pi hat here. I want to know what this distribution is, so I can then work out from this idea of what the likely values of this thing are. So let's have a look at some results here, some math stuff here. Sums of random variables. If I've got two independent random variables, y1, y2, and the mean is mu I for these, and variance is sigma I squared. So y1 has mean mu1, and y2 has mean mu2, and the variance is sigma 1 squared and sigma 2 squared. So if I look at the sum of these variables, weighted sum over here, the means will be the same with the same weights there. The same equation holds for the means with the particular weighting over there. If I'm looking at the variance of these things, of the sum, because variance deals with square quantities, I'm going to get the squares over here. So a squared and b squared, I've missed the square there. A squared and b squared there. And then I've got a squared times sigma 1 squared plus b squared times sigma 2 squared. I get the sum of squares of the quantities multiplied with the variances there. And I can extend this to more than two independent random variables. And the idea mainly here is they're independent, and that's why there's simplification. If these things weren't independent, then that still holds, but I get some more things in here than I've got there. I've got some idea of how the dependence works between those two variables. I've got to build that in there. Some of you might have seen this before. If you haven't, it doesn't matter, but I will be dealing mainly with or only with independent situations, so I can hold this. I can extend this to more than two. In particular, if I extend this to IID, independent and identically distributed random variables as well, with mean mu and various things are squared, this is what we call a random sample. I've got observations from some population with particular characteristics over here, and I'm pulling them one by one here, and I've got the same distribution for each of these things I'm pulling out. So this is my random sample, and y bar here is my sample mean, which is essentially add them all up, divide by n. Now it's not so hard to show this. The variance, the mean is fine, so we can do the calculation here. If I want the expected value of y bar, then the expected value of y bar, I think on the next, no I haven't here. E of y bar here, remember this thing means sum essentially, so this is just y1 plus y2 up to the yn divided by n in the end. So this is saying I want the mean of this y1, y2 up to the yn added up over n over here. Now the n on the bottom is a constant, so it doesn't change the expectation, it comes outside. And I've got now the sum over here, so this becomes e of y1 plus the mean of the second one, and all the way to the last one. And each of these things have the same mean. Each of this is equal to mu. So I'm adding this mean n times, and I get n times the mean, n times mu, and I'm dividing by n as well. Well, after I cancel those off, I get the mean mu here. So a sample mean, which is a random variable because it depends on my sample, has the same mean as my population mean, the thing I'm trying to estimate. But the variance is a little different. The variance of y bar is sigma squared upon n, and that works in a similar way. So if we look at the variance of y bar here, that's the variance of y1 plus y2 all the way to yn over n. Now the constant term here gets squared when it comes outside the variance. And then I have variance of the first one. Because of independence, the variances simply add. And each of this is simply sigma squared. So I'm adding the sigma squared n times. I've got 1 over n squared to start off with here, and I've got these variances n squared, n times sigma squared. I'm adding the sigma squared n times. One pair of n's will cancel off from here. One pair will cancel off here, and I get sigma squared upon n. That means that my variance of my sample mean depends on the sample size. As my sample size increases, this will decrease. So a sample size of 10 will have a larger variance than a sample size of 100 for the sample mean I'm getting. It changes very fast here with n, you can see. So those two results are important. Now, more than that, so far what I've got here is that I can work out the mean of the sample mean and the variance of the sample mean. The next result actually extends the idea a bit further and says I can do a bit better than I can actually find the distribution as well. So I wanted to know what the distribution of sample means is going to be. And this is where this central limit theorem comes in. Some of you may have seen this before. It says if I've got y1 to yn are again the iid random variables with some common mean, because the iid they must have the common mean and common variance, and I put y bar as the sample mean here, then for n large enough, what I've done here is I know that the y bar here, it has mean equal to mu, and it's got variance equal to sigma squared upon n. So I'm taking the mean away from there. So I'm saying y bar minus the mean. I'm dividing by its standard deviation, which is the square root of this thing. Take a square root of this sigma squared over n, and the sigma squared has root sigma and the root of n stays. That's how I get this term over here, sigma on root n. In other words, what I've done is I've standardized the sample mean. Standardizing means taking the mean away and dividing by the standard deviation. What I'm saying is that that thing is approximately normal, normally distributed with the mean 0 and variance 1. So when you standardize something, you're actually turning the mean to 0 and the variance to 1. So I'm standardizing. That means I've got my standardized random variable, has standardized sample mean, has mean 0, variance 1, and is also approximately normal. And when I say large enough here, n bigger than or equal to 30 is sufficient for a good approximation. So I now have, for the sample mean, I've got the mean, I've got its variance, I've got its distribution as well, and that allows me to do things with it. So let's have a look to see how this works. If I look at my estimator here for the proportion here was a sample mean. We know that. We did say this is essentially y bar, my sample mean here. What I'm saying here is that I know from before the mean of yi is the Bernoullis are just pi, and the variances are simply pi times 1 minus pi here. But using my above results here, what I'm going to get here is the mean of y bar here. Pi hat is y bar. The mean of that's going to be mu, and the variance should be sigma squared upon n. This is my sigma squared here, and this is essentially sigma squared upon n. So I'm treating the proportion as a sample mean. That's what this is really all is. And so that means if I take a look at this y bar and standardize this, this becomes approximately normal for large enough n. So for n large enough, and usually the idea with this is that it's not just bigger than or equal to 30, because the problem is what happens is when pi is too close to 0 or too close to 1, yeah, that's usually the problem. If it's too close to 0, then I'm going to get something that is not quite going to be good enough, and I'll show you what I mean by that. But as long as I've got these situations happening, then my pi hat is approximately normal as I've got there. That's the mean mu, if you like, and this is sigma squared upon n. Or, if I put this as z here, as pi hat minus the mean over pi 1 take pi on n square root of, I've standardized this, I've taken the mean away and divided by the standard deviation, this is approximately normal node 1. Either way works. Now, as we said earlier, the mean of my pi hat is equal to pi, and this is the thing I'm trying to estimate. That's why we say that pi hat is unbiased for estimating pi. On average, it's the same value. The variance here becomes smaller and smaller as my sample size gets larger, and the distribution is approximately normal because of my central limit theorem. So let's do some simulations to see how this works out. So you can simulate it yourself. Here is my code somewhere there. I'm going to create myself samples of size n from Bernoulli distributions. I'm going to create many samples of that size, and I'll take a look at the sample mean from each of those samples. I'll look at my proportion there from each of the samples and plot them all out and see what they look like. So here's the code here. Setting the seed idea is if I repeat this particular code, I get the same answers. In other words, if I set the seed here, then every time I simulate, I get the same data back again. That makes it reproducible. Otherwise, I get different data every time. So I'm setting the seed here. My true value of pi is 0.45. And I'm going to take a look at 1,000 observations for each sample. This is my per sample. And I'm going to take a look at altogether 10,000 samples. So here's my matrix of observations. I first of all initiate them with zeros to get my storage set up. I've got n observations as rows, so I've got my columns is the number of samples here, each sample that way, and that way I've got my observations here with rows. So here's my simulation. R binomial. R stands for random, and the binomial is for binomial, as you'd expect. This is how many I'm going to simulate, and this is my number of samples, which is just 1 because it's Bernoulli, and this is my pi. And I'm doing that 1,000 times, and I'm going to repeat that whole thing 10,000 times. That's my loop here for I in 1 to n, 1 till about 10. In this case, I've got 10,000 is my n. And so there's my data here. This is my 1,000 samples across the columns, and my rows here contain 1 sample each. This, in other words, this row here is sample number 1. Let me see. No, that's not the case. This is the other way. I've got the thing in rows. This is my sample number 1. Sample number 2 all the way to sample 1,000. So over here, this way, I'll have 1,000 observations. It's 10,000. Here I've got 10,000 samples altogether. If I look at the mean of each of those columns, I'll have the mean of 1,000 observations here. In other words, my proportion is based on 1,000 observations here. So I can find the means. Not so difficult to do. And the command I need is column means. Column means gives you the column means of the matrices by columns. And here some of the means I've got over there, the first few and the last few there. Now, I can find the mean of all these. This is the mean of my sample of sample means, if that makes sense. I've got all these 10,000 samples from each of the samples. I've got a sample mean there. I've got a proportion there. I average them all out. That is my mu hat. And I've got here the sigma. I've got this 10,000 observations, 10,000 sample means, or 10,000 proportions I've estimated. I want their standard deviation, and I've worked that out as well here. And you can take a look at the values here. Here's my histogram of those. 1,000 sample size of 1,000, 10,000 of those. You'll find it's not very far from normal. It's pretty close, actually. Yeah, it's not going to be exactly normal ever because it's data-based, but it's still pretty good to a normal distribution here. What you'll find is the mean here should be close to. I started off with a mean of 0.45. Where are we? 0.4544. So this mean should be close to 0.4544. And the standard deviation should be this sigma upon n idea, right? So the standard deviation here, and you'll see this in the next slide, my mean is 0.4542, not very far off. And my standard deviation here is 0.0002, which is essentially this idea of pi times 1 minus pi over n, the number of observations here. That's what this looks like here. And this, of course, was 1,000. That's 0.0002, and that's what I have over here, not very far from that at all. So the numbers work out as well. Now this is one simulation. You can do many of these kinds of things and see the difference. I can change the sample size, I can change p if I like, but you'll find that you'll get similar pictures. You can go online, you'll find many of these as well. The idea I'm trying to illustrate here is that the central limit theorem does look reasonable, and you can see it's not very far from normal at all. And so in practice, you just use those as the results we've developed for our ideas. So previously, when I did the hypothesis test, I used the binomial distribution because essentially my x was binomial. Years ago, and I'm going back to this sort of 70s, 80s idea here, before we had these computers and all this power behind computing, we couldn't find, well, we used to use binomial tables, and the tables were very sparse. As you can, if you've seen tables, you'll know that. And machines couldn't handle, the small calculators we had couldn't handle things like 1,000 or 10,000 for the binomial distribution as the n. But now they can. R can take something like about 30, 40 billion or something, or trillion. And that's way, way more than we'll ever need. So in those days, we used to approximate the calculations by using the central limit theorem, and actually finding p-values by using the normal distribution. We didn't have a choice then. But now we do. So we can use the exact, as I did before, the binomial test, and I found the p-value from the binomial distribution. Otherwise, I can still use this idea here, and you'll see the difference in a second. I'm looking still at the same hypothesis. Pi is 0.5 is less than 0.5. I have here, previously my test statistic was the observed number of successes, 480 out of 1,000. Now I've got my proportion, sample proportion here. I can compare this directly with that value, essentially, what I'm saying over here in the end. And so if the null hypothesis is true, then I know that this thing is approximately normal, not 1. So I can find the probability as a p-value. P-value is a probability here straight by using the normal distribution. If I do that, what I'm after here is p-value is probability that pi hat is less than 0.5, which comes to this kind of calculation here. Now, I can do that, and I've done that here. So normal distribution, the norm here is what R uses for normal distribution. P here stands for probability, so it's finding the probability of being less than equal to, or less than. So what I get here is probability of being less than 0.48. This is the mean, and this is the deviation. I actually haven't done this calculation here. You can put in straight away the values. I've got my pi hat was 0.48, and my pi was 0.5, which I've got in here, and my sigma is pi times 1 minus pi over n square root of, and that probably comes to 0.1029. What I had before from the binomial distribution was 0.1087. You can see this is not very far from that, although this is more accurate. But in the scheme of things, as I'm looking at this, it's accurate to the first 2 or so decimal places, and the conclusion is the same in any case. So the p-value here still is going to be bigger than 0.025, so there is insufficient evidence against the null hypothesis. Either is good enough in our case. I prefer to use the exact binomial test when I can do that, but you can do this as well, and that's also fine. In the end, when we get to trying to fit in models, R does things by normal distribution anyway, makes no difference. But in small sample sizes, you might find a difference if you don't use the exact test. Any questions so far? I'm speaking for an hour or so now. All right. Now, confidence interval. The idea with confidence interval essentially is, I know the distribution of my pi hat is normal with pi as the mean, and the variance is pi 1 minus pi over n here. What I'm going to do is work out essentially the idea here is, if you've seen this before, then this will be easy for you. But otherwise, I'm looking here to see, there's my pi hat. What are the possible values around that I can get here? So I get probability of 0.95 in the middle here. And if I do that, that's called a 95% confidence interval. If I can change that my level of confidence to 99%, I get 99% confidence interval. If I do this from the Z tables, I can essentially just work it out from there as a calculation. And so what it becomes here is, from a calculation, I get this formula in the end. Is pi hat minus, because all I'm doing is I'm with the standard normal distribution, I'm trying to unravel that. I'm saying, all right, in the normal distribution, to get a probability of 0.95 in the middle, I require a value of 1.96 here and negative 1.96 here. That means if I transform that, this is normal not 1. If I transform that to something else that is normal but not with the same mean, but says the mean here is, let me call this mu hat, and the variance here is sigma hat squared, then what happens is, I just take the 0 goes to the mean, so I have the mean there, and I go 1.96 on the other side with the standard deviation, which is sigma hat, and I go 1.96 on the other side of this as well. So it's also going to be mu hat minus this value, 1.96 times sigma hat, and those points here transformed back to that normal distribution with a different mean and different variance gives me my confidence interval. This z alpha upon 2 is a bit tricky, but all it means here in the symbolic sense is that all I've got is normal distribution, and the probability here is 1 minus alpha. So by symmetry, what's left over here is alpha on 2, and what's left over here is also alpha on 2. And so this value here I call this the critical value, and the critical probability here is z alpha on 2. So alpha on 2 probability in the tail, and the value there is the z value, is a critical value here. I can calculate that from R very easily. You don't require to understand the formula. What you do need to know is how it works in R. So look at this if you want to be carefully. But the way it works is this. Of course, I've got sigma hat there, right? Because in the original normal distribution thing, I've got pi there, which I don't know. So I can't use, when I'm trying to find the sigma hat here, I can't use pi because it's unknown to me. So I use the pi hat in its place as well. So what I get here is, when I use pi hat here instead of pi, I call this the standard error of my estimator, pi hat. So it's the same pi 1 minus pi over n square root of. It's the standard deviation. If I put pi in there, if I put pi hat there as observed value, it becomes what we call standard error. Again, this is more terms and statistics to make sure it's not confusing one from the other. One's based on the exact value, which is pi. One's based on data values, which is pi hat. And so I call this the standard error. And so the confidence interval works out essentially, as always in this case, is going to be the observed value or the point estimate that you've got, and around there you build yourself a little interval. So it's a critical value from the z distribution times the standard error you've got there. And I've got a 1 minus there. I would rather put it as alpha only. This is some notation that's different from what I'm used to, so I'll take that off. So I've got some critical error from the z distribution and then standard error. Now, regardless of what you're trying to estimate, it always has this particular formulation. So whenever I'm trying to estimate something, I want is point estimate, some number that comes from some z distribution, then times the standard error. Every confidence interval is based and calculated in the same way. What might change is this thing where it comes from. Usually it comes from normal distribution, but it can come from other distributions in some other scenarios. But by and large, this is how we actually work out confidence intervals. So if I continue with that, what I've got here is, in this case, I've got my significance level is 0.05. So that corresponds to a 95% confidence interval. So this is for a two-tail test. So the idea is, if I'm looking at a two-sided test, what I'll have anyway is, in my calculation for confidence interval, if I'm looking at 95% confidence interval, and that is 0.025, and in the lower tail also I've got 0.025. I'm using a symmetrical distribution over here, symmetrical calculation for confidence interval. If I'm looking at a one-sided test, then my p-value is compared to 0.025 only. It's two-sided test, is both sides, so either way it's consistent. So I'm looking here, my probability for the z 0.975 here. So if this is 0.025 there, and that's 0.025 here, the middle bit is 0.95. That's my confidence level. So all that below here is 0.975, and so R requires that probability to give me the number here, which is about 1.96. That's my Z value, Z 0.025. So R works it out as this idea of Q norm. So Q stands for working out the quartile, if you like, finding, in other words, here I have a probability, I want to find the appropriate Z value. So I've got 1 minus alpha, alpha has been set as 0.05 over 2, so this essentially this should be 0.975. If I make this 10%, the number I get is 1.64. So it's 95% here, or taking a look at the tails as 0.05, the value is 1.96. If I make it 0.1 in the tails, in other words, then I've got 0.95 in the formula there. This is 0.05 here instead of 0.025, and this is 0.05 as well. There's 10% in the tails, and I've got 9% there, so on that bit here is 0.95, and that's what I've got put in my formula there. So I get from there my Z value is 0.1645. As I increase my confidence level, my Z value is going to be bigger and bigger and bigger because I'm going outside in the tails. In this case, I just did the calculation by hand there. So I've got my observed value is 480 out of 1,000. That's my p hat. Its standard error is pi hat times 1 minus pi hat over n square root of. That's my next calculation. That's my standard error. And my lower value is pi hat minus the 1.96 times standard error. And the upper value is pi hat plus 1.96 times my standard error. And my limit here comes to 0.449 and 0.510. There's my interval. Now, this statement here that's made is 95% confidence that the value of pi lies in the interval. Now, people question this all the time, saying, what do you mean by 95% confidence? And the idea here is that, well, actually, it doesn't mean anything at all. When I say 95% confidence, if I ask you, what does 95% confidence feel like? So in some ways this is useless. In other words, it's got some use nonetheless. My preference would be to use this idea here. Pi hat is 0.480, and the standard error here is 0.0158. That tells me how accurate my estimate is. It's within 1% or so, almost 1.5% or so. As opposed to somebody else's estimate that may still be 0.48. For example, if I base it on a sample of size 100, then I've got, say, 48 observations, or 48 is my number of yeses, then my pi hat is still 0.48, but my standard error will be larger in that case. So I know my estimate is better than yours because it is a smaller standard error. But if I use this idea of confidence interval, and I compute my confidence interval on a sample of 1,000 and yours is a sample of 100, then my interval will be narrower than yours. Mine is more accurate, either way. So my preference is to do this, but this is pretty common in the literature, and people use it all the time. So if you're asked to calculate one of those, you just calculate that and then done. Report that as normal. All right. So from what you find is that my hypothesis test for this same data was that I didn't reject it. We failed to reject it. In other words, I didn't reject the hypothesis that pi was actually equal to 0.5. And you also find that 0.5 is in there. So if I'm looking at a 95% confidence interval and a 2.5 level of confidence significance in a one-sided test, they're the same, equivalent. If I don't reject H naught, I'll find the value of my null hypothesis, the value for parameter will be in the interval as well. They're consistent. So they're both equivalent in that sense. If I'm looking at a two-sided test of 0.05% significance, then again 95% confidence interval will contain my null hypothesis value. So that's how these things work. As I was saying earlier, this idea of 95% confidence interval, this is just a bad word. It's nothing to do with confidence, because confidence is something you can't measure. But what I can say here is, in terms of some quantification, it does mean that 95% of confidence intervals that are generated from samples of size n. So in other words, in the case of our example, if I take a look at 1,000 samples of size 1,000, and I have many such samples of size 1,000, and I compute 95% confidence intervals based on those, then 95% of those intervals will contain the true value of the parameter. So if I generate my samples from pi equals 0.5, and I find 1,000, and take a look at samples of size 1,000, and I have, say, 100 of those samples, then 95 of those samples, 95% of the confidence intervals I get from the samples should contain 0.5. Now, you might guess that sometimes 96, sometimes 93, but otherwise, this is what you're looking at. About that much is what you'll be looking at. This is what this is the interpretation of confidence interval, and this is what's called the frequentist approach, because here I'm looking at the thing as a frequency-based thing, frequentist. The other ways of working these things out as well, in statistics, but this is what we'll be doing here for the moment. And here's an example of doing that. What it means is that if I get this kind of confidence interval worked out here based on the same sample size, then some of them will miss it. So the black line here is my actual mean. You see, some of them will miss it, some of them will contain it. So here's one that misses it. Otherwise, about 95% of those, in other words, out of 20 essentially, you expect to miss one or so. And that's what the diagram they illustrate, that you'll miss one or so. In 25% is essentially just one. So you might miss one, sometimes you might miss two, but you wouldn't miss too many. So here's a summary of what you've done so far, and you can look at that yourself. There's 2 slides of it, essentially. Now, there is one thing you will find that I do have. I'm not sure whether it's in the lab actually this morning. I didn't check it very carefully because I put it in a bit of a. But what you'll find is it says 2 by 2 contingency tables and difference of 2 proportions. I haven't done those yet. I've just done this. My idea is to do this a bit more slowly so you get the idea of this. You might find the lab contains questions on the next 2. That's fine. We'll cover those next week in the lectures, and we'll move on from there. Any questions so far? So you have a test due this week, as I was saying to somebody else earlier, maybe to you as well. Your idea isn't, and I just said earlier, your idea isn't to find the MS model, so don't struggle too much with it. Illustrate that you understand the modeling concepts, you know, or you can work out how to transform variables, and then see from there what you get. And don't be late with the assignment, please. It's due at about 11 or something in midnight, close to midnight, 11 p.m. on Friday. If you do that properly and in time, then I'll get the markers to mark it, and we hope to return the thing within a week or so. So you've got your feedback and some marks from that before your next assignment is due, your next test, which is going to be week 5. Yep. It says either a PDF or a Word document. I would very much prefer if you started using the R Markdown, you use those instead. It makes it far easier for you as well, and it generates the the PDF file straight away as well. Yeah, it's anyway, as long as, well, if you can always do things in Word and cut and paste, but it's much more painful. If you change things and you actually submit the wrong file to me, then all I've got is the wrong file. That's all I mark, right? But if you do it in R Markdown or in a book or whatever, that's fine. Whatever format you use is fine. You'll get a PDF from there anyway. Any more questions? Yep. I have an example file there. Just use that, cut and paste. Yeah, change your name to my name. No, my name to your name. Yeah, put this as test 1 or whatever else, put the date in there, and you want an article, this can all be the same. And you can put in here introduction, whatever else. No, I'm not wanting all that stuff. Later in the semester, we'll start writing reports instead of just what you're submitting here. So you've got in the question, in the assignment or the test, you've got parts A, whatever else, until I think E or G or something. Just put part A, part B, or whatever else. Answer those things as you go through there. I think you'll find that this will work quite well and very easily. All you do is, as I was saying, go to NIT and produce a PDF from there. Yeah, and it'll work very well. Any more questions? So I've done a bit less this week because I don't want to overwhelm you too much. So next week we'll cover contingency tables and take a look at some other tests as well, and then we'll cover a bit more material next week in that case, once you've got the basic ideas out of the way. All good? All right, we'll see you next week in the lab if I'm there.
I had a quick look at the solutions for the first
Lab.
and
Yep.
In the model fitting portion, the lengths all displayed a kind of exponential squared kind of feature, and when you modelled them again, you only modelled the 2 lengths and left one out.
Well, the third one wasn't significant.
Well, that was why.
Yeah.
After the modelling, it's still in the model after you.
To start off with, then I omit it. I omit the model. As I reduce the model, I take out length 3.
It was the one you omitted later on.
Yeah. But because you're saying that the lengths all seem to have this exponential distribution, instead of exponentiating each of those, I took the log of the weight instead.
Yeah, I was wondering about that.
Because that is one transformation as opposed to more transformations.
Because what I did was take the log of the response.
Yeah, but that doesn't work, you see, because you want the exponential. You want essentially what you want is you're trying to say that y is equal to e to the x. Yeah. That means the log of y is equal to x. You're trying to model it that way instead of modeling it the other way, right?
Yeah.
That makes it linear in x over here with taking the log. And of course, you've got more than that here. You've got this one here, and you've got the next one here as well. If I log this instead, I get the log of each of these things over here. Yeah.
Yeah. So if you, when you're taking a transformation of one of the predictor variables, do you leave in the untransformed version as well?
No.
You take it out.
Yeah.
Take it out.
No, the only case you wouldn't do that is if you take a look at say polynomial transformations. So if I'm looking at something like y equals, say, x squared, then I leave the x term there as well. The idea is that you leave the lower order terms in the model unless it's reason to take them out. If you include higher order terms, you must also include lower order terms, unless it's reason to take them out. Now, of course, when I'm going to square root, that's different. I don't require x there anymore. I drop that. That's different. Yeah. I dropped out. If I'm looking at square root, I drop out the x, unless the x was in the model as well for some other reason. But if you're looking at polynomials of this kind, then I'd put the lower order terms in there as well. If you use x cubed, you must use x squared and x as well. Now, sometimes you take them out for other reasons, because it may be I'm looking at, for example, the volume of a log, yeah? and I'm looking at the volume with respect to the length and the radius. The radius will be, the volume will be depending on r squared there, right? So I'll use r squared, not r in that case, in the model. There's a reason for that. Yeah, context space. Who's next?
For this question, it says to describe the graph, like
Yeah.
what kind of
What do you say?
information?
What do you see? Is it log exponential? Is it looks like a pattern there? Is it too much variation there? What do you see there?
Oh, so like, I have a graph.
See, if you've got a graph that looks like this, yeah. You may say, all right, this seems just some trend. Linear, maybe quadratic, maybe some curvature there as well. So I've got something like this. Nothing mainly, but an outlier.
Oh, so
Yeah, if I see something like this, I'm seeing groups in the data. Yeah?
okay.
Those are the kinds of things you explain. And of course, I can also say, well, there's some variation. I might have, for example, data that might look like this.
So do I write like the R code?
You write the R code for the plots and give me the codes, but then you describe what you see, and you
Like that's
also
common.
you'll have the graphs as well in there. You can comment on the graph. Here's my graph. This is what I see from the next graph. This is what I see.
Okay.
Yeah.
So is that also worth mark?
Oh yes, yes,
Thank you.
certainly worth
So
mark.
comment also worth some
Absolutely,
marks.
the comment's worth. That's where the marks are. Not this thing. You tell me what you're actually seeing. Yeah.
Yes.
There's a quick question, like, was like type 1 error?
Yeah.
Exactly. This one. How
Type 1 error is essentially, it's a probability. The way it works is, type 1 error is when you reject a true null hypothesis. Right?
okay,
So we're not going to go into the details for that, maybe not, at least not yet. So type 1 error is essentially the probability of rejecting a correct null hypothesis, and you want that to be minimized. And that essentially is going to be less than your significance level. Yeah. Type 2 error is not rejecting a false null hypothesis.
thank you.
Yeah, good.
Two questions. So firstly, when you have a model and you're removing variables from it,
Yeah.
you select them just based on
P-values, largest one first.
p-value largest one first. Okay. And you remove them until one of your variables is significant.
No, you remove them until no variables are not significant. You remove them until all the p-values are bigger than, less than 0.05, for example.
Okay.
Yeah?
Also, I was trying to install the Markdown thing, and there was an issue in the packages. Have you seen that before? So trying to, as soon as I click near, it says it needs to install a package. I
Okay.
try to install it and there's an error. And I've just Googled it a bit. I was just wondering if you'd seen that error before.
Okay, what do you say?
Oh, never mind. I think it's actually
Yeah.
one.
Yes, problem with your for there. Good, excellent.
Clarify on the previous slide also, because okay,
Yeah.
just wondering in terms of when you mentioned this part when you say examine the plots, then the comments were length 1, length 2 had some quadratic
Looks like
relation.
quadratic exponential, yeah.
But if that's the case, then why is the length 3 considered a quadratic equation as well?
Well, they're all similar, aren't they?
They're all similar.
Quadratic or
But,
exponential.
yeah, but the thing is, your comment only mentioned length 1, length 2, never mentioned length 3.
Did I not do length 3 in the model at all?
No, we did not.
I'm surprised. I'm not looking back
Yeah,
at that.
so that's why.
It should be link 3, that should be it as well.
Yeah, so in this model, length 3 is missing, but in the
Next
next
one
one,
I've got link 3 in there, right?
yeah, so when you lock this one, then length 3 came back in.
Yeah.
So I was wondering whether is
No, I think what I did was, when I was doing this earlier, I think length 3 wasn't significant in my earlier model. And that's why I look at it. I'll look at this again, but I think that's what I found. I believe that length 3 was not significant in the earlier model, so that's why I took it out. But yeah, exactly right. When you start looking at this, after the first model, I should be looking at my residuals and plots before I do that. And I can decide what transformations to use before I start putting my next model in there. So yes, you should put length 3 as well in that case.
the original fit-up model, the residuals against fitted values, in terms of the
See, residuals versus fitted values will give you some idea of how good the model is in the end, right? Is the model good enough or not, or is something missing? But you can't then work out how it behaves with respect to each variable until you plot residuals against each variable separately.
but because